Previously on Chemistry Z, our heroes journeyed to the mountains of Group 1 to discover the secrets as to why they increase in reactivity as you move down the group. But now, our heroes journey across the periodic table to the ruins of Group 7 where they will encounter the deadly halogens. Will our heroes be able to pattern displacement reactions with aqueous salts? All this and more will be revealed in today's exciting episode of Chemistry Z. Here are the retrieval questions for this lesson. I have the periodic entries for lithium and potassium on the side. You know what to do. From the Group 1 video, we saw that potassium is more reactive than lithium. Check that video out to find out why. The electronic configuration for potassium is 2881 and potassium has 20 neutrons in its nucleus. We call Group 7 elements halogens. They are the second to last column on the right hand side of the periodic table. Based on their position, decide if you think halogens are metals or non-metals. Of course they are non-metals. And if we look at the melting points, green, and boiling points, red, of period 3, you can see that like all other non-metals here, halogens have relatively low boiling points. Looking at the electronic diagram of halogens, you can see that bromine and iodine looks crazy. You're not expected to be able to draw bromine and iodine at GCSE. If anything, they'll only get you to draw the outer shell electron. So let's look at the dot and cross diagrams which you are meant to be able to draw then. Since we are in Group 7, they have 7 electrons on their outer shell. Remember from our video on noble gases that all elements want to be noble gases.
I wanna be like you. I wanna walk like you. Talk like you too.
And for these elements, they can share one of their electrons. Now around each atom, they have 8 outer shell electrons, just like every noble gas except for helium. This is why halogens travel around as diatomic molecules. Remember, di means 2, like dioxide, 2 oxygens, diatomic molecules. Also, this is why halogens do not conduct electricity. They do not have any free electrons that can move throughout their structure. Alright then, we have this table showing the melting and boiling points of the different halogens. I've got these challenge questions for you to have a go at. Pause the video and do your thing. We see that melting point increases as you go down the Group 7 elements. Remember that minus 220 is colder than minus 101. The same is true for boiling point, it increases as you go down the group. This next one could be a little bit tricky because room temperature is defined as 25 degrees Celsius. So you have to look at the melting and boiling point and have 25 degrees in your mind.
See, when I'm telling you that what they want is to bring us here and punish us, you did not believe. Can you see?
This isn't punishment. If these type of questions confuse you, let's just simplify it by drawing out a table like this. Jaden.
Yo.
When does fluorine melt?
Minus 220.
So we put in the solid box minus 220. This means that any temperature below minus 220 is solid for fluorine
It's a liquid in between the two numbers then, right?
That's absolutely right. So what is fluorine at room temperature?
25 degrees is higher than its boiling point, so it's a gas.
You're right. Good work. You lot at home can work out why these are the answers to chlorine, bromine and iodine at your own time. Just use the same method I showed you. Halogens react with hydrogen gas, but some are more reactive than others. Fluorine makes hydrogen fluoride. Chlorine makes hydrogen chloride. And bromine makes hydrogen bromide. Look at the differences between each molecules. I'm only showing the outer shell electrons here. Think about what attracts electrons. Now answer this challenge question. Which halogen would you expect to be the most reactive? It's hydrogen fluoride. Since halogens need to gain an electron, the smaller the atom, the more reactive it's going to be. This is because the outer shell is closer to the positive nucleus and so it experiences a greater electrostatic attraction. It's then easier for it to gain that electron. This is why fluorine is one of the most reactive elements, if not the most reactive element in the universe, because it just moves around and yams the electrons from anything. Also, there is less electron shielding. This is why bromine is so much larger than fluorine. It has 2 more electron shells inside it. Remember that we are only showing the outer shell electrons here.
Okay.
Here is the general word equation for the reactions of halogen and hydrogen. They produce hydrogen halides. The "ide" bit of the name is important, as you shall see. Spend some time completing the word equations. For the first one, we formed hydrogen fluoride, so we must have used fluorine. Okay, notice the change in the name. So using that pattern, bromine and hydrogen must produce hydrogen bromide. And for the last one, we made hydrogen iodide, so we must have reacted iodine and hydrogen. Let's now look at the symbol equations for these reactions. Listen, just like with the group 1 reactions, you just need to memorize the red bits. The black X is the halogen in each example. Spend some time completing the symbol equations using what we have here. (2HBr) gas for the first one, F2 gas for the next one, and 2HI is the final one. Make sure you do not mix up the subscript numbers and the large numbers, okay? Oh, and some of you are probably wondering why iodine and bromine are gases in this reaction. It's because we have to heat them up past their boiling point to get them reacting. Remember, the reactivity decreases as you go down the group. So we need to heat up the bromine and iodine to get them to react with the hydrogen. But the fluorine that reacts quickly with hydrogen, no long thing.
You don't know nothing, but I'm gonna tell you something. I'm saying, hey yo.
The next set of reactions we have to look at are halogens reacting with aqueous salts. But first, we should define what a displacement reaction actually is. A displacement reaction is when a more reactive element displaces a less reactive element from its compound.
I don't care what it's called. When Papa visits here, I'm going to tell him that you people commit all kinds of abomination in this house.
Okay, I'll break it down some more. Will Smith, please forgive me, I love you, this is all for science. In a displacement reaction, we have a compound. and a reactive element. The less reactive element will be replaced like so. This is all there is to it. No need to get tangled in madness. I'm sorry, Will. I'm so sorry. Let's say our starting compound was potassium bromide, and we add chlorine, which is more reactive than the bromide ions. Our end product will therefore be potassium chloride and bromine. Again, notice the name when we have the halogen by itself and when it becomes a halide ion. The ene turns into an ide. What about if we add potassium chloride and bromine together? Think carefully about this one. What do you expect will happen? There will be no reaction. No, wait. I didn't lie to you guys. Remember that the element has to be more reactive. Bromine isn't more reactive than chlorine. For group 7, as I said, reactivity decreases as we go down the group. So fluorine is the most reactive here and iodine is the least reactive here. Using that logic, which of these reactions will react? And as an extension, what are the products called? Since fluorine is higher than chlorine, this reaction will happen to form sodium fluoride and chlorine. Chlorine is higher than bromine, so this reaction will form magnesium chloride and bromine. Bromine is higher than iodine, so this forms lithium bromide and iodine. The next one, there is no reaction because fluorine and fluoride ions have the same reactivity. Iodine is lower than chlorine, so there's no reaction here as well. And finally, bromine is higher than iodine, so this reaction will form potassium bromide and iodine. Lovely jubbly. A simple displacement reaction you may do in class would look something like this. You have a spotting tile with 3 different compounds. This column is sodium chloride, this one is sodium bromide, and the last one is potassium iodide. So we've got our different halide ions going down in each column. The easiest way to react our halogen to the compound will be to dissolve them in solution. Hence we've got chlorine water here, bromine water here, and iodine solution here. After pipetting each solution into our compound, we notice that some of them have changed colors. This is the color of iodine solution. So no reaction has occurred. This is what we expect because iodine is less reactive than both chlorine and bromine, and it has the exact same reactivity as iodide, so there is no reaction there. So all 3 of these had no reaction.
I'll drill y'all. Stop playing with my name. I ain't gonna say it no more.
The only one that changed here is the potassium iodide, since that's the only one that bromine water can displace. The last one is a little bit difficult to see, but we see a slightly yellow-green solution here because bromine has been displaced and an obvious reaction over here. Spend some time actually understanding what's going on here. This is just the practical version of the theory we just looked at before. Because the different halogens are colored, that's why the reaction looks this way. when we produce something that's got iodine in it, it's slightly dark brown. When we produce something that's got bromine in it, it's a yellowish color. And when we produce something that's got fluorine in it, well, you can't really see anything here. Now, just like with the group 1 elements, you expected to be able to explain the trends down group 7 for 5 or 6 marks. Spend some time answering these 4 questions. The force attracting the electrons and protons to the nucleus is the electrostatic force. Both fluorine and chlorine will gain 1 electron. Chlorine will experience more electron shielding. We can see that extra electron shell there. Since the outer electrons in fluorine are closer to the nucleus, then they experience a greater force of attraction, and so fluorine is more reactive. And there we go! Lesson done!
Fatality.
We looked at the trends in group 7 and the different reactions of group 7. Use the timestamps to skip to where you need to go. Collect the flashcards and revision timetable in the description, and I'll catch you guys in a bit.